Welcome, friends, followers, future followers, and curious people. This channel is dedicated to dark screen ASMR to optimize bedtime listening by decreasing light while you relax or sleep. Today's dark video is reading 50 physics ideas you really need to know by Joanne Baker. Number 1. Mach's principle. A child whirling on a merry-go-round is tugged outwards by the distant stars. This is Mach's principle that mass there influences inertia here. Through gravity, objects far away affect how things move and spin nearby. But why is this, and how can you tell if something is moving or not? If you have ever sat in a train at a station and seen through the window a neighboring carriage pull away from yours, you will know that sometimes it is hard to tell whether it is your own train leaving the station or the other arriving. Is there a way that you could measure for sure which one is in motion? Ernst Mach, Austrian philosopher and physicist, grappled with this question in the 19th century. He was treading in the footsteps of the great Isaac Newton, who had believed, unlike Mach, that space was an absolute backdrop. Like graph paper, Newton's space contained an engraved set of coordinates, and he mapped all motions as movements with respect to that grid. Mach, however, disagreed, arguing instead that motion was only meaningful if measured with respect to another object, not the grid. What does it mean to be moving if not relative to something else? In this sense, Mach, who was influenced by the earlier ideas of Newton's competitor, Gottfried Leibniz, I'm absolutely positive I'm saying that wrong and I'm so sorry. Gottfried Leibniz was a forerunner to Alfred Einstein in preferring to think that only relative motions made sense. Mach argued that because a ball rolls in the same way whether it is in France or Australia, the grid of space is irrelevant. The only thing that can conceivably affect how the ball rolls is gravity. On the moon, the ball might well roll differently because the gravitational force pulling on the ball's mass is weaker there. Because every object in the universe exerts a gravitational pull on every other, each object will feel each other's presence through their mutual attractions. So motion must ultimately depend on the distribution of matter or its mass, not on the properties of space itself. Mass. What exactly is mass? It is a measure of how much matter an object contains. The mass of a lump of metal would be equal to the sum of the masses of all the atoms in it. Mass is subtly I can't say that softly, I'm sorry. Mass is subtly different from weight. I did it. Weight is a measure of the force of gravity pulling a mass down. An astronaut weighs less on the moon than on Earth because the gravitational force exerted by the smaller moon is less. But the astronaut's mass is the same. The number of atoms he contains has not changed. according to Albert Einstein, who showed that energy and mass are interchangeable. Mass can be converted into pure energy, so mass is ultimately energy. Inertia. Named after the Latin word for laziness, is very similar to mass, but tells us how hard it is to move something by applying a force. An object with large inertia resists movement. Even in outer space, a massive object takes a large force to move it. A giant rocky asteroid on collision course with the Earth may need a huge shove to deflect it, whether it is created by a nuclear explosion or a smaller force applied for a longer time. A smaller spacecraft with less inertia than the asteroid might be maneuvered easily with tiny jet engines. Italian astronomer Galilei, I can never remember. We'll go with Galileo Galilei, proposed the principle of inertia in the 17th century. If an object is left alone and no forces are applied to it, then its state of motion is unchanged. If it is moving, it continues to move at the same speed and in the same direction. If it is standing still, it continues to do so. Newton refined this idea to form his first law of motion. Newton's bucket. Newton also codified gravity. Codified? Wow, I swear I'm good at reading, except when I put the pressure on myself. Alright. Newton also codified gravity. He said that masses attract one another. An apple falls from a tree to the ground because it is attracted by the Earth's mass. Equally, the Earth is attracted by the apple's mass. But we would be hard-pressed to measure the microscopic shift of the whole Earth towards the apple. Newton proved that the strength of gravity falls off quickly with distance, so the Earth's gravitational force is much weaker if we are floating high above it rather than on its surface. But, nevertheless, we would still feel the reduced pull of the Earth. The further away we go, the weaker it would get, but it would still tweak our motion. In fact, all objects in the universe may exert a tiny gravitational pull that might subtly affect our movement. Newton tried to understand the relationships between objects and movement by thinking about a spinning bucket of water. At first, when the bucket is turned, the water stays still even though the bucket moves. Then the water starts to spin as well. Its surface dips as the liquid tries to escape by creeping up the sides, but it is kept in place by the bucket's confining force. Newton argued that the water's rotation could only be understood if seen in the fixed reference frame of absolute space against its grid. We could tell if the bucket was spinning just by looking at it, because we would see the forces at play on it producing the concave surface of the water. Centuries later, Mach revisited this argument. What if the water-filled bucket were the only thing in the universe? How could you know it was the bucket that was rotating? Couldn't you equally well say the water was rotating relative to the bucket? The only way to make sense of it would be to place another object into the bucket's universe. Say the wall of a room, or even a distant star. Then the bucket would clearly be spinning relative to that, but without the frame of a stationary room and the fixed stars. Who could say whether it was the bucket or the water that rotates? We experience the same thing when we watch the sun and the stars arc across the sky. Is it the stars or the earth that is rotating? How can we know? According to Mach and Leibniz, motion requires external reference objects for us to make sense of it, and therefore inertia is a concept is meaningless in a universe with just one object in it. So, if the universe were devoid of any stars, we'd never know that the Earth was spinning. The stars tell us we're rotating relative to them. The idea of relative versus absolute motion expressed in Mach's principle have inspired many physicists since, notably Einstein, who actually coined the name Mach's principle. Einstein took the idea that all motion is relative to build his theories of special and general relativity. He also solved one of the outstanding problems with Mach's ideas. Rotation and acceleration must create extra forces. But where were they? Einstein showed that if everything in the universe were rotating to the Earth, we would indeed experience a small force that would cause the planet to wobble in a certain way. The nature of space has puzzled scientists for millennia. Modern particle physicists think that it is a seething cauldron of subatomic particles being continually created and destroyed. Mass, inertia, forces, and motion may all, in the end, be manifestations of a bubbling quantum soup. There's a quote here from Isaac Newton in 1687 that reads, "Absolute space of its own nature, without reference to anything external, always remains homogeneous and immovable." And at the bottom of the page, there's a timeline. So, 335 BC, Aristotle states that objects move due to the action of forces. 1640 AD, sorry, I had to pause the video because one of my cats was walking around screaming, and then the furnace turned on and a train went by. We're right by tracks, so I'm just going to start on the timeline again. I'm so sorry. Alright, so 335 BC, Aristotle states that objects move due to the action of forces. 1640 AD, Galileo formulates the principle of inertia. 1687, Newton publishes his bucket argument. 1893, Mach publishes The Science of Mechanics. In 1905, Einstein publishes The Special Theory of Relativity. Now there's one little blip here about Ernst Mach. So this says 1838 to to 1916, as well as for Mach's principle. Australian physicist Ernst Mach is remembered for his work in optics and acoustics, the physiology of sensory perception, the philosophy of science, and particularly his research on supersonic speed. That's cool. He published an influential paper in 1877 that describes how a projectile moving faster than the speed of sound produces a shock wave similar to a wake. It is this shock wave in air that causes the sonic boom of supersonic aircraft. The ratio of the speed of the projectile or jet plane to the speed of sound is now called the Mach number, such as Mach 2 is twice the speed of sound. I actually never knew that. I never knew what Mach 1, Mach 2, I didn't know. I just knew it meant really fast. And, faster than the number before, I assumed. But I really like that. That's fascinating to me. Well, there we go. I will do the second of the 50 physics ideas you really need to know as soon as I get another chance. That's all the time I have today. I'm sorry for any cuts in the video/audio when I had to rapidly pause to deal with sudden noises or situations going on in the house. Hopefully it didn't throw off the overall quality and effect of the video. Alright, well, thank you for joining me on our journey today. I hope you found it pleasing and effective. Feel free to like or follow if you enjoyed our time together. And goodbye for now.